This is a patch of grass, but there is a rabbit in the grass. In order to see it, you have to cross your eyes. If you do it properly, you should be able to see the 3D image of the rabbit popping out of the screen. Images like this are called autostereograms or magic eye pictures. You can pause the video here if you want to try and see the rabbit yourself. In this video, I will try to design an algorithm to recover the 3D object hidden behind the magic image. Let's assume that we know nothing about how the magic eye images work, so we have to decide how to start our approach. We suspect, however, that the magic effect has something to do with the image being periodic horizontally. Indeed, the picture seems to repeat itself over and over again, here, 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 and here. Every time, the pattern seems to start over. So an idea that we could try is to get an inverted, transparent version of the picture and just lay it on top of the original one. For those of you who are old enough, this should remind you of an old-fashioned paper photography negative film. We can now slide the negative along the original picture and see how it compares. Yup, this is a rabbit. It seems that the background of the rabbit gets repeated every so many pixels, while the interior part of the rabbit gets repeated over a shorter distance. During this video, we will be sliding images a lot, so to make things a little easier, we will take the part that comes out from one side and place it back at the beginning. In more technical terms, we will take the images to be periodic as a whole. I will not try to go into the details of why our brain decides to see these patterns as an actual 3D image of a rabbit. Let's just notice that if we place some transparent screen between our eyes and some nearby object, the lines of sight from each eye will intersect such screen at some distance from each other. This distance becomes larger if the object we observe is further away. In this sense, the patterns that repeat over a shorter distance tend to appear closer to you than those that repeat over a larger distance. Let's start writing some equations. The magic image, as any image, can be represented by a matrix. Actually, by 3 matrices, corresponding to the 3 primary colors red, green, and blue. However, we still want to make our life simple, so we will work on the grayscale version of the picture. In this case, each element of the matrix is a pixel in the image. The elements take values between 0, corresponding to a black pixel, and 1, which is a completely white pixel. The indices I and j of a pixel are the numbers of the row and column of the pixel. As I said before, we will impose the pictures to be periodic as a whole, so we identify the elements beyond the height or width of the image with the ones in the other side. We can now make a new matrix by taking the difference between the original magic matrix and the right-shifted version of itself, that we will call D. To get a general idea, let's plot the average of the elements of D as a function of the shift number n. Well, there's clearly something going on here. The large dip at n equals 200 tells us that a large portion of the image doesn't change much when shifted by 200 pixels. This is actually the background of the rabbit image that we have already seen when playing with the negative film. We will call this shift NB equal to 200, as it is the shift of the bottom layer of our 3D object. Looking at the plot, the higher slices of the rabbit seem to be around smaller pixel shifts, down to some NT equals to 160, which is the N shift of the top layer of the rabbit. You can observe that the layers of the 3D object usually appear as lower values of the average of the D matrix elements between NT and NB. If we display the matrix D as an image for an N shift of 200, we can check that indeed we recover the background of the rabbit, as we saw before. In order to display the matrices as images, I'm actually rescaling its elements so they are all between 0 and 1. If we move to a smaller shift, say n equals 166, we can start to see a slice of the rabbit. This is a level set of the depth function, the set of points which appear at a constant distance in the magic image. Now I would like to somehow extract the slice from the picture in a reliable way. Here's a very simple method that I have found to work quite well. If we zoom in at a point inside the rabbit slice, we see that the image looks very smooth in there. On the other hand, the picture is quite rough in the regions outside, with a lot of spatial variation. In particular, we have taken squares of 7 by 7 pixels around each point. If we compute the standard deviation on the values of the first square, we just get 0, as all the pixels had the same value. On the other square, we get a rather high value of 0.21. So let's define a new matrix that we will call S, whose elements are the standard deviation taken on a neighborhood of each element in the D matrix. We take a neighborhood of radius r as the set of pixels that are at most r steps away from the central pixel. For our experiment, we will always use r equals 3. If we plot the matrix S as an image, normalizing it first from 0 to 1, we do see that the rabbit slice appears very dark, while the rest of the picture has some tone of gray. If we keep changing the shift N, we can scan over all the slices of the rabbit, as in a medical CT scan. Now I would like to join all of these slices in the same picture and get a depth map of the full rabbit. For each point, we will try values of the shift n in the range between nt and nb, and identify the value of n that gives the smallest standard deviation. We will call this value n minimum, which of course depends on the pixel position, so it also carries the indices I and j. For points corresponding to the bottom layer of the 3D image, we should hopefully get the smallest standard deviation when n is close to its largest value, nb. For the points in the top layers of the rabbit, we should get n minimum to be close to nt. Once we have the values of n minimum for each pixel, we can define the recovered depth map like this. You can take some time to convince yourself that for n minimum equal to nb, rij will have a value of 0, which is a black pixel, and for n minimum equal to nt, we will have a white pixel. All intermediate values of n between nt and nb will end up as equally spaced shades of gray. Let's go back to our original autostereogram. By computing the R matrix, we see that the rabbit magically appears. The left part of the picture is too close to the border, so it doesn't look good. We can remove this part and apply a Gaussian blur to make it a little softer, and we obtain the final depth map of the 3D rabbit. The light parts of the map appear to be closer to you, while the darker parts appear further away. We can even plot the depth map as a two-variable function, so we can see more clearly its three-dimensional shape, with a rainbow color map. In the last part of the video, I will discuss a way of doing the opposite process. Suppose that you have a depth map of some 3D object, in this case a cube, and the texture, in this case a stone wall, and we want to produce an autostereogram that encodes the cube in a stone wall texture. Clearly, we have to modify the texture in some way, so that the patterns repeat in the horizontal direction every so many pixel positions. The period of pixel repetition should be larger for far points of the cube and shorter for closer points of the cube. First, we have to choose the shortest period for the top layer, nt, and the longest period for the bottom layer, nb. In this case, we will choose the same values that we had in the rabbit, so NB equals 200 and NT equals 160. We also have to make sure that the height of both the original depth map and the texture image are the same, as measured in pixels. This may require some resizing. Then we can create the magic image in a recursive way. The first NB columns of the magic image will just be identical to the texture image. Then every pixel will be filled with the same color as the one shifted n positions to the left. The value of n for each pixel has to be some integer value between nt and nb, depending on the original depth map matrix. Again, you can take a moment to check that this definition of n of ij is indeed an integer that takes evenly spaced values between nb and nt as the depth map goes from 0 to 1. Applying all this to our cube and our stone wall, we get the new magic image. Pause the video if you need it to see that it works. If we try to recover the object by the algorithm we used in the first part of the video, we get an imperfect version of the original depth map. I find it quite impressive that the retrieval of the 3D object from the magic image takes quite a large amount of mathematical operations when solving it in a computer. But we can still solve these images in our heads in less than a second by just looking at them. I really hope you liked the video. Don't forget to write a comment, subscribe, and see you next time.